Hello students, how are you? So let us start our today's class. So in the today's class, we will cover the filling of electron. So if I just recall about the previous class, in the previous class we got the atomic orbital shapes, right? We got the shapes of the atomic orbital. Now we are not filling it. I would not say exactly that filling it. We are saying that the probability of finding two electrons is maximum in that atomic orbital. Okay, clear? No, but for our simplicity, we will not take that probabilistic part when we move to this filling of orbital actually, right? So when we are filling, we will not take the probabilistic part. We will take the deterministic part that, okay, we are sure that our electron is in that orbital. Clear? Okay. So filling of electron is basically building up of our electron, and the most basic and the fundamental idea behind filling is that they are filled in the increasing order of energies, right? How they are filled? They are filled in the increasing order of energies. So what does this mean? It means that the one with the lower energy is filled first and the one with the high energy is filled later on. So that construct a series. So how do you construct it? So you just arrange your atomic orbitals in the increasing order of energy, and then you start filling the electron. Now remember one thing again from a previous class, which is very important, that if you are treating a single electron system or a hydrogen like atom, then the energy order would be different. Like 1s will have the lowest energy, then 2s and 2p, okay, 2s and 2p, both of them will have the same energy. Then 3s, 3p, 3d, all the three of the subshells will have the same energy, and 4s, 4p, 4d, 4f will have the same energy. So this order is important here. Clear? So this order is very important here. So how do we fill it? In the increasing order of energy. Clear? So this is for hydrogen atom, but for multi-electron system, these rules doesn't count. Okay, so we have to now arrange them in the increasing order of energies, and it is not simple as it seems, right? So you can't say that 1s, 2s, 2p, 3s, 3p, 3d. So that is not the order, because the shape and size are continuously changing, and those affect the order. Okay, those affect the order. Clear? So how do we fill the electron? First of all, from the lowest energy to the highest energy, and that is decided that which orbital will have the highest energy and which orbital will have the lowest energy. So it is decided by the n plus L rule. Okay, n is here the principal quantum number and L is here the azimuthal quantum number. So we take the n plus L value, and the one with the lower value of n plus L has the lower energy. The one with the higher value of n plus L will have the higher energy. If two orbitals have the same n plus L value, then in that case, what do? We take the one as the lower energy, which has the lower value of n. Clear? Is this point clear? Okay, got it? Next is this order, which is important. Okay, this is the order which is important for the increasing energy. Now if you just take out the value of n plus L, then this order fits very well. So for this orbital, 1s orbital, n plus L value is what? N value is 1 and L value is 0. So that would give n plus L as 1. Okay, so this is the minimum value you can get. Then we have 2s. So it will have n plus L value as 2. You can count it. N has a value of 2 and S has a value of 0. So 2 plus 0 is 2. About 2p. So p has L value is equals to 1 and n value 2. So 2 plus 1, 3. So n plus L is 3. Now here also 3s also will have the same n plus L value. So I have told you that if two of them have the same n plus L value, then the one with the lower energy of L is n is taken the lower value. So out of 2s and 3p, 2p has a lower value of n, so it will fall before, then will come the 3s. Clear? Then again n plus L. So n for 3, n is equals to 3, 3p, n is equals to 3, and L is equals to 1. So 3 plus 1, 4. Again 4s will have the same n plus L value. So again we will look upon the n value. So in this way you will go on rearranging this atomic orbital and you will get a series of increasing energy. Now how the electrons will fill? So as I have told you, first the 1s will be filled, then the 2s will be filled, then the 2p will be filled, and they will be filled until and unless it is completely filled. So we'll see that all those things in the next part. So starting from the top, the direction of the arrow gives the order of filling of electron, that is starting from the right top to the bottom left. So we are referring to this diagram here. So you can see this is the arrow diagram. That is a kind of shortcut. If you don't have time to calculate the n plus L value, just write in this way: 1s, 2s, 2p, 3s, 3p, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, and start drawing curved lines like this. Okay, and wherever the curved line goes, the order stays like that. So 1s, 2s, 2p, 3s, 3p, 4s, 4p, 3d, 4p. In this way you go on filling the electron. Clear? Now, so here is the n plus L value of all of this. So you can see it is 1, 2, 3. Now this both have 3. So since 2p and 2s, 2p has the lower value of n, so it goes up. Again 3, 4. Again they have the same n plus L value, so again 3p goes up. Then 5 and then 5. Again the 3d has a lower n value and it goes up it goes down in the energy. Clear? Okay. So this is the trick to remember this, or you can either, if you have time or you are good enough to calculate the n plus L value quickly, then you can do in this fashion also. You can just simply calculate n plus L values and compare the values. Clear? Okay. Now, next is Pauli exclusion principle. What is this Pauli exclusion principle? So this is very important. It says that two electrons cannot have the same set of all four quantum numbers. So what is the meaning of this? So if you have electron and the value of n, L, m, and ml. Okay, so we have the four quantum numbers: principal quantum number, azimuthal quantum number, spin quantum number, or the one is orbital. Yeah, okay, azimuthal quantum number. Then we have angular momentum quantum number, and at last we have spin quantum number. Okay, so if all of these four values are same, then it is wrongly written in some way. So we can not have the same value of all the atomic orbitals same, right? So one of the value at least will be different. So this should be clear. What? That one of the value should be different out of the four quantum number. Clear? The number of electron to be filled in various orbital is restricted by exclusion principle given by the Austrian scientist. So what does it mean? You cannot put 3 electrons in an orbital. So this principle says that. So because if you do so, then all the values are already same: n value, principal quantum number value, azimuthal quantum number value, ml value. All 3 are same. The only difference was that they both have the same spin. But since if we just put 3 electrons there, then what will happen? Then 2 of the electrons, because only 2 options are present, up or down, then 2 of the electrons will have the same spin, and that is completely wrong. Okay, so this was given by scientist Wolfgang Pauli. Now, according to this principle, no 2 electrons can have the same set of 4 quantum numbers. Is the same thing written here. Okay, next. So the same thing is written here also, that only 2 electrons may exist in the same orbital if they have the opposite spin. So this give rise to the filling of electron, the way we fill of electron. Okay, so in an orbital we know that 2 electrons can be filled, and there are 2 options of filling the electron: up spin or down spin. Now if you are filling the 2 electron in the same orbital, means n value, that is principal quantum number value, L value, that is azimuthal quantum number value, and ml value, all these values are same. Now the only remaining different value is spin quantum number. Now if you fill the both of the electron with the same spin, then they will have the same 4 set of quantum numbers, and this is not possible. So you can think of it in this way, that the similar particle is having 2 different energy. Okay, so you can think in this way also, that a single particle is having 2 different energy. It is that similar to. Okay, so the same thing is written, that they can have the same value of n, L, and ml, but they will have the opposite value of spin quantum number, or either they will be identical. So the restriction was of course imposed by Pauli exclusion principle, and it was based on the number of electron in a people, and it helps in calculating the capacity of electron to be in a subshell. Clear? So from subshell, 1s comprises 1 orbital. We know that because 1s orbital contains only 1 orbital, and thus the maximum number of electrons represented in 1s orbital can be 2 in p and d subshell. The maximum number of electron could be 6 and 10 and 10 and so on, right? Okay, the maximum number of electron in the shell principal quantum number is equals to 2n square. We know this formula, very primitive formula. Now this rules of Hund's rule of maximum multiplicity. Okay, so this deals with the electron, filling of electron in the orbital belonging to the same subshell. So suppose you are filling the electron in the same subshell, then in what way you will feel that? Okay, so earlier the Pauli exclusion principle was kind of putting a restriction on that if two electrons are filled in the same orbital, they cannot have the same spin. Okay, so this was the first Pauli exclusion principle example, and the four quantum numbers cannot be same. Next is Hund's rule of maximum multiplicity, which says that if you are filling the orbital belonging to the same subshell, okay, it start pairing of electron in the orbital belonging to the same subshell does not take place until each orbital belonging to the subshell has got one electron each. So what is the meaning of this? So basically it is related to pairing of electrons. So if you have to fill a subshell, then you will start filling it singly first of all, and after some time you have to put the second one. Okay, after some time, not so once it is half filled, if that subshell is completely half filled, then we start pairing those electrons. So we are talking about one subshell. Clear? We are talking about one subshell. Now in p orbital there are 3 p orbitals, px, py, pz, and 5d orbital, dxy, dyz, dxz, and dx square minus y square, and f orbital. Therefore the pairing of electron will be in the p, d, and f orbital with the entry of 4, 6, 8 electron. Clear? Now it has been observed that has a completely filled and fulfilled orbital have lower energy. So this is very, very important point. You will see the use of it in your chemical periodic table, right? In the periodic table. Now the distribution of electron, which we have seen just now, is called the electronic configuration, and if one knows all the rules, then you can fill it very quickly. Now the electronic configuration of different atom can be represented in two ways. What are the two ways? First is the notation that we use, SPDF. Second is the orbital diagram. Okay, so the used one is what? Orbital notation is used. So if you just start filling the electron, then how it will be filled? 1 here, then 2 here, then 3 here, and then the pairing will take place. Okay, and then the pairing will take place. So in the first notation, the subshell is represented by the creative letters letter symbols and number of electrons present in the subshell, and depicted is as a superscript like A, B, C. Okay, now the similar subshell represent 4 different shell, and it differentiated by writing the principal quantum number before the respective subshell. Clear? Now in the second notation, each orbital is represented by a box, and the electron is filled in the form of up spin and down spin. The advantage of second notation is that over the first is that it represents all 4 quantum numbers. Clear? Now the hydrogen atom has only one electron which goes in the orbital with the lowest energy, that is 1s. Now the hydrogen atom is having electronic configuration of 1s, meaning that it has no electron in the 1s orbital. Clear? The second electron in the helium orbital can occupy 18 orbitals, right? So the second electron in helium can occupy 18 orbitals in what? 1s orbital. Now its configuration is 1s2. So this is very important, that its configuration is 1s2. Clear? Now next. So in this way we can fill. So for hydrogen, 1 will be filled with the upfield. For helium it will be 1, 2, and in this way we fill the orbitals of the electron. So however, it takes the next available notice for 3, 4 finish. Clear? Got it? So it makes the next available choice for the namely 2s orbital. Now let us see some configuration here. So lithium. Okay, we start with lithium. Now first of all we will arrange. We have 3 electrons, so they can be filled in 2 orbitals only, because one orbital has 2 electrons and it will need one more orbital to get filled. Okay, now you have to fill 2 orbitals. So what are the 2 orbitals with the lowest energy? So it is 1s and 2s. Okay, so this is the Afbau principle. Now next, how we'll fill it? then we have what? Then we have the Pauli exclusion principle. Means in the 1s electron, in the 1s orbital, we will field 2 electrons and both with the opposite spin, and then we will go to 2s and field 1 electron. Clear? Got it? Okay. Now, what about the configuration of, so before moving to beryllium, I want to ask you that how you will fill the electron in the 1s. So first you will singly fill it and then you will double it. Okay. So you can't go from singling it 1s and then singling it for 2s. So what you have to do, if you have to pair it up, just pair it up in the 1s only. So the 1s is a lower energy and 2s is a, 1s is a higher energy and 2s is of a lower energy. Now taking about the configuration of beryllium, so again 1s2, 2s2. Next is the next 6 element boron. So if you talk about boron, 1s2, 2s2, 2p1, then 1s2, 2s2, 2p1, then 1s2, 2p2, then 1s2, 2p2, and 2s2 and 2p3. Okay. So we go on filling the electron in the 2p orbital until it is fully filled. And we got the configuration of neon 1s2, 2s2, 2p6. Now this process is completed with neon atom, right? It is completed with neon atom. So in this way we fill the electrons, right? So you can see here that, okay, we for a lithium we have the single upside, then downside, then single. Then beryllium we have upside, downside, again upside, downside. This is the algorithm. For the B, that is boron, upside, downside, and in the next p orbital upside. Okay, so if you just move this next one, okay, so in this case upside, so this both are what? These both are having the same number of electrons, boron and carbon. Okay, next again for nitrogen, see, it is filled. Firstly it is half filled. You can see very clearly that the orbital is firstly half filled. The 2p orbital is half filled, and after half filling it, if you just move on to a next atom, then it does not go to the later orbitals. Then instead of that, it gets paired up. Okay, what does happen? It gets paired up, and then we have fluorine, and then we have neon. Clear? Okay, got it. So if I talk about the electronic configuration of sodium, so it is 1s2, 2s2, 2p6, and 3s1. If I talk about argon, then 1s2, 2s2, 2p6, 3s2, and 3p6. So this is the way of writing it. Okay, so this is the way of writing it. So what are we doing here? So we know that the electronic configuration of AR is, that is argon, is this. Okay, so we will, instead of writing the whole configuration, we will simply write it as AR, and then the remaining one are placed. Okay, then the remaining one are placed. Clear? So like example, we have a sodium. So sodium has what? One extra electron other than the this. Okay, the neon. So you can write it in this way, that neon with the braces and electron. Similarly, here we have what? Here we have neon, and that is helping to write the name of argon here. So neon 3s2, 3p6. Clear? So this is the electronic configuration. We do the electronic configuration in this way. Now, the electron in the completely filled shell are known as cold electrons, and the electrons that are added to the electronic shell with the highest principal quantum number are called as valence electron. For example, the electron in neon are the core electron, and the electron from sodium to argon are the valence electron. So in the potassium and calcium, the 4s orbital being the lower in energy, then the 3d orbital is occupied by 1 and 2 electron respectively. Clear? Okay. Now what is ground state configuration? It basically refers to the most stable, or the one which is having the lowest energy. Okay, so that is recognized as ground state. So the electronic configuration follows these rules, and they are filled in this way. Now, one more very important thing: why is the half filled and full filled stable, right? So why is the half filled and full filled more stable than the partially filled? What is the reason behind it? So we can have the application of it also. So when you will see in chromium and copper, so instead of say moving on to 4s electron, this is getting back to 3d. Okay, so it is not 4s to 3d, it's 3d8. If you just calculate the n plus l value, then you will find that the n plus l value of 3d is more than a 4s. But still, the 4s is half filled, means the lower energy is not filled first, then the higher energy is filled. Clear? And therefore these two configuration, that is 3d4 and 4s2 and 3d9 and 4s2, this both are unavailable, right? This both are unavailable, means they are wrong. Okay, they are wrongly written, whereas this one is rightly written. And why is this so? Because in both these cases we are getting half filled orbital, or in this we are getting fulfilled orbital, and they have more stability. For that reason we are seeing this kind of configuration. Now the completely filled and completely half filled orbital are stable due to the following reason. The first is symmetrical distribution of electrons. So you know that nature loves symmetry. So if something is symmetrically distributed, then it will have lower energy. Clear? It will have lower energy, but the shielding of one another is relatively small and the electrons are more strongly attracted by the nucleus. The first is what? Symmetrical distribution of electrons. It leads to symmetrical distribution of electrons. Next is exchangeable energy. So what happens that if it is half filled, means there is a chance that two of the electrons will have the same spin. So this is the first point, and they both can interchange their position. So there is a kind of delocalization of the electron which leads to the stability, and this stability is coming as a factor of the exchange energy. Clear? So exchange energy is maximum, and so it is stability. Now the exchange energy is at the basis of Hund's rule that electrons which enter orbital of equal energy have parallel spin as far as possible, because we filled it firstly half filled, so that all of them are the parallel spin, and then we start pairing it. Now the extra stability and half filled orbital is due to following three reasons. First of all, as I have told you, it will have more exchange energy. Second is smaller coulombic repulsion energy, and third is relatively small build shielding. So these are the three factors that says that the half filled and full filled are more stable than the normal one. Okay, so this is the way we represent the exchange energy. See, this electron can exchange with this electron can exchange with this electron, this can exchange with this one, and this can exchange with this one. So in this way we kind of find the stability in case of half filled subshell. Okay, clear? Why? Because two electrons can interchange their position because of the same shape and the same size. So these are the electronic configuration that we have of the initial elements. You can see it in a quick fashion. Then I will move it. Okay, so this is the electronic configuration of the remaining one. So you can see sodium, potassium, aluminum. Okay, so in this way it is filled slowly. 1, 2, 3, 4, 5, 6. Okay, it is filled slowly. Then it almost got interrupted in this point. Okay, at this point it got interrupted. Then we have this electronic configuration, which is based on the n plus L value and the n value of large or small. Okay, if n value is large or small. So atoms are, this is about the, so let us get to summary. So first of all, it was believed that atoms are the building blocks of element, and they are the smallest particle that can react, okay, that are chemically inert. And it was given by John Dalton in 1808. But towards the end of the 19th century, it was proved that atoms are divisible and consist of three fundamental particles, that are electron, proton, and neutron. Okay, so this discovery of subatomic particle led to the proposal of various atomic models to explain the structure of atom. So Thomson in 1898 proposed that an atom consists of a uniform shape of positive electricity with electron embedded in it. So you can think of it as a chemistry, as a Christmas pudding in which the cherries are present as the electron. Now this model, in which the mass of the photon is considered to be evenly spreaded, the atom was proved wrongly by the Rutherford experiment. Means it was totally proven wrong. Because why it is proven wrong? Say, because if the lawn tennis was spreaded so, then it would not have been developed, right? Now Rutherford concluded that atom is made up of teeny positively charged nucleus at its center with electron revolving around in circular orbits. So Rutherford, which represents the solar system, was no doubt a very improved theory. So this could explain many of the things, but all of the things are not explained by this planetary method. Okay. Further, it was silent about the structure of atom, about the distribution relative energy of the electron. Now in the next class we have seen that okay, these difficulties were countered by the Rutherford by giving his model. Okay, and later on Bohr postulated the model, which is very important for your exam point of view. Clear? So it calculated the energy of electron in various orbits, and for each orbit predicted the distance between the electron and nucleus. Second is, though offering a satisfactory model for explaining the spectra of hydrogen atom, could not be explained by the multi-electron system. So it was now also it is not explainable for the multi-electron system. Now in a Bohr model, an electron is regarded as a charged particle. Okay, we know that well confined in a circular orbit, the wave character of the electron is ignored in the Bohr theory. So we know it very well. And orbit is clearly different path, and this path can be absolutely defined only if both the expectation and the velocity of the electron at the same time are unknown. Clear? Got it? Now the Bohr model not only ignores the dual behavior of electron, but also it contradicts the Heisenberg uncertainty principle. Therefore, Erwin Schrödinger in 1926 proposed the famous quantum mechanics, which helps us in calculating, or you can say knowing the energy of the levels. Clear? Now this this equation incorporates de Broglie concept of wave particle duality and is consistent with the Heisenberg uncertainty principle. So the principle that was given by Erwin Schrödinger, it was compatible by both de Broglie and the Heisenberg uncertainty principle. So it says that when a H operator operates on the psi, it gives you back the energy plus the energy of that psi. So this quantized states and corresponding wave function, which are characterized by a set of 3 quantum numbers, arises as a natural consequence of solution of the Schrödinger equation. Clear? So they are arising as a consequence of the what? As a natural occurrence in the solution of the Schrödinger equation, and the solution is giving us these constants. Clear? Now the restriction on the values of this quantum number are also naturally from this solution, so they are only distributing this factor, right? So we can see that we have put the limit while deriving the formula. Now according to the quantum mechanics model of the atom, the electron distribution of an atom containing A of wide electron is divided into shells. Okay, what does it say? According to the quantum mechanics model, the electron distributed of an electron contains a number of electrons, it is divided into shell. Now the shell in turn consists of subshell, and the subshell consists of orbital where the electrons are kept. Now while for hydrogen and hydrogen-like atom, all the orbital have the same energy if they are in the same principal quantum number. But for other one, we have the n plus L rule, which determines which will have lower energy and which will have higher energy. Clear? So this was all about today's lecture. So with this, I end my lecture. Thank you.